So in the last class, we start talking about linear functions, and later on, I'm going to cover applications of linear functions. Okay. So linear function is just saying that if you have linear expressions in the form of mx plus b, right? For m is different from zero. If you stick this with an output, then you have a linear function. Basically, it's just saying, can you find an equation of a line? So hopefully, after this lecture, you could be able to distinguish between linear expression, linear equations, and linear functions. Okay. So some of the terminology we already covered in lecture 6, which is finding the equation of the line, right? M in this case is the slope of the line. B in this case, the y-intercept. There are some of the common forms that get used in finding the equation of the line, the point slope form, the slope intercept form, the general form. You have the horizontal line, vertical line. In lecture 6, we also cover how to find the equation of the line if the line is parallel to another line or if the line is perpendicular. Another concept that we covered last time is the average rate of change of linear functions. Okay. We say that, okay, the average rate of change has the same formula as finding the slope of the line going through 2 points. We did a couple of examples on finding the average rate of change, and one of the very important notes on the average rate of change of a linear function is that for linear functions, the average rate of change is a constant. Okay. So in example 1, you calculate that you have the slope or the average rate of change is changing as we calculate different data points. So we say that the average rate of change is not a constant for the first example. But for the second example, when we calculate the rate of change for different data sets, we see that we have the same number, which is negative 0.25 in this case. And therefore, we conclude that from this data, this is the average rate of change is a constant. Therefore, you can use a linear functions to fit into this data set. Any questions? We good? So that what we covered last time. Let's continue with some applications for linear functions. So when we learn about functions, a lot of time we use the function or the graph, the function to fit into some data set or to model some problem, real life situations. So in this case, the model that we want to look into is the linear depreciations, right? When you buy something, let's say a computer, let's say a car, let's say a machine, right? So the value of the machine will depreciate over time. Okay. Now, can we calculate that change given some data information? So for example, for this example, what do you say that they have an insurance company purchases an SUV for its employees. The original cost is $30,500. The SUV will depreciate linearly over 5 years, and will then have a scrap value of $10,000 answering the following questions given the information. Okay, what is the rate of depreciations? And then from there, can you calculate or can you find a linear equation that describes the book value at the end of t years for t between 0 and 5. And then at the end, using the information from part B, can you calculate the book value at the end of the 3rd year? Okay. So you have some data information. You have some information. Can you calculate the average rate of change? Given the information, very important information is that the SUV value depreciates linearly. Based on that, based on the information, you can calculate the rate of depreciations. Based on the information, you can also calculate the equations that you can use to fit into this data sets. And from these functions or the equations that you come up with, you can use that to make further predictions. Okay, that's the application. Now, from the given informations, you need to collect or gather some information for our calculations. Okay. So it say that the original cost is $30,500. And then after certain years, after 5 years, the value of the SUV go down to $10,300. Okay, so that's the two data points that you have for this calculations. The first data point is the original time and the original value. Okay. The second data point is after 5 years, time equal t equal to 5, and the current value after 5 years, or the value after 5 years. You good? All right. So for part A, you need to write down the informations that given to you. So you have 2 points or 2 data points. The first one is the original time, so therefore t is equal to 0. So the first component of the point is time component. And the second component of the point is the value of the SUV, which is $30,500. All right. So here you have the original time and the original value. After 5 years, you have, so t equal to 5, which is the first component of the point. You have the value of the SUV is 10,300. So given 2 points, you can find the rate of change. Remember, the model that we're using is a linear model, I said in the problem. So the rate of change, or the rate of depreciations, right? So you just basically calculate the rate of depreciation using the formula y2 minus y1 over x2 minus x1. Given that this is x1, y1, this is x2, y2. So y2 is 10,300 minus 30,500, altogether divided by 5 minus 0. That's the setup. Any questions on that? Good. All right. Now, if you do the calculations correctly, you should get negative 4,040. Now, if this is a real world situation, if you work at a car dealership or insurance company for that matter, you cannot give your boss this number. Okay. You have to write in certain sentence to draw the conclusions from these calculations. Okay. So the conclusion is that the rate of depreciations, right, is $4,400 per year. You with me on that? Not a negative value, but in words, you say the rate of depreciations is $4,040 per year. In other words, or another way to say or conclude this calculation is that the value of the car, of the SUV, reduce at a rate of $4,440 per year. You with me on that? So that's another way to conclude this calculations. the price of the SUV reduce at a rate of $4,040 per year. You with me on that? So that's how usually when you read the document, it means that when you do a calculations. Okay. And depreciation also means reducing. All right, so that's how you have to draw the conclusions in the real life situation. You cannot just give a negative number. Okay. All right, so now that part A, you calculate the rate of depreciations. Now for part B, given the linear equation that describe the SUV book values, what is the value of the SUV at certain time t? All right, so that means in part B, just tell you that can you find the equation of the line going through the 2 points? That's it. So that's how you find the equations to fit into this data set. So the linear equations or the linear function, linear equations, we need to find is v of t equal to mt plus b. Or I could say linear function. So just write it down, bear with me here. I explain the notation a little bit. So the capital V just tell you it's just short of the abbreviations. The abbreviations for value. Okay. So the value depends on T, the parameter T, which is time. M is the slope, right? Or the average rate of change that we just calculated, which is negative. And B is the y-intercept, which we use the data points. You with me on that? All right. So capital V in this case, it's just value. It's just put it in. You can use capital B or F of T. Just like that. All right. So the point now is that you already have the slope, which is equal to negative. Bear with me here. Still negative because we do calculation. We're not drawing any conclusion just yet. Okay. So the value of the slope or the average rate of change is negative 4,040. Okay. Where M is equal to negative 4,040. And V of T represents the value of the SUV at time t. Now with the informations that we got so far, then V of T is equal to negative 4,040 T plus B. Okay, so you have the slope. And you remember this is an equation of the line went through 2 points. Right. You have 2 data points earlier. Right. these are the two data points we collected from the problem. Good. All right. So therefore, you say that n v of t passes through one of the points, right? So in this case, I'm going to choose the first point, 0, 30,500. Then we get that 30,500, which is the output, just substitute into V minus 4,040 times 0 plus B. So therefore, B is equal to 4,000, sorry, to 30,500. Now we have enough information to say that the linear equations is, or function is, V of t equal to negative 4,040 t plus B. In this case is for 30,500. All right. We good? Any questions? So I hope when you go back and review, or 10 years from now, 5 years from now, when you go back and read this materials for some weird reason, but I hope that you don't just see this as a formula, so as a problem, math problem that doesn't mean anything. It's true. It's not something abstract, but it's actually tell you some information, tell you a story here. So in this context, given this linear functions, the original value or the original book value of the SUV is 30,000, and the value will decrease over time at a rate of $4,040 per year. So that's the story that I see from this form. You good? All right. So for a math formula, when you look at the math formula, there's a story behind it. Hopefully that we learn enough information, we have enough knowledge to depict the formula in a way that makes sense to us. All right, so that's the linear equation. Now that part B. For part C, what will be the SUV book value at the end of third year? Okay. So good. We're going to use these functions to calculate the value of the SUV when t is equal to 3. You okay with that? Okay. So this process in part C that we're going to do is called interpolation. New one. Thank you. I didn't know. I don't remember I have them. All right. So interpolations. You have a functions, right? And you want to calculate something within this time frame from 0 to 5. So in this case, you want to calculate the value of the SUV when t is equal to 3. So 3 is between 0 and 5. So this process is called interpolations. If you want to calculate the value of the SUV when t is equal to, let's say, 7, which is out of the domain between 0 and 5, we call that process extrapolations. extrapolation. You see the difference between the two processes because we have t to be equal to 3, which is in between 0 and 5. So do interpolations. So C at the end of the third year, t equal to 3. The value of the SUV is, so V of 3 equal to negative 40 times 3 plus 30,500. If you do the calculations correctly, you could get $18,380. So you conclude that, you write conclusions that the value of the SUV after the third year is $18,380. So the value of the SUV after the third year is $18,380. So hopefully this example is not too overcomplicated for us to do, right? Understandable. So this is a applications for linear functions. So they use a lot of this type of approximations or calculations in economics and statistics. All right, so let's cover one more example on linear depreciations. Any questions on example 3? Any questions? All right, example 4. Suppose that a company has just purchased a new machine for its manufacturing facility at $120,000. The company chose to depreciate the machine using the linear depreciation method over 10 years. Write a linear model that expresses the book value of the machine as a function of its age, X. All right. So in part A is contain a lot of steps to get to the answer. Okay, so that is to get a linear model, you need to have a slope. Right? To calculate the slope, you need 2 data points. And can we collect those data points from the problem? Okay. So the initial book value of the machine is, say, V equal to $120,000, right? When t is equal to 0. So originally, the value of the machine is $120,000. Now, after 10 years, what is the value of the machines going to be? We're going to make these assumptions, okay? The value is going to be equal to 0, but have no more value at all after 10 years. Okay, so that's the assumptions that we need to make. So the book value of the machine after t equal to 10 years is v equal to 0. So from this information, we say that, okay, now I have two data points. The first data point is 0, 120,000, and the second data point is 10, 0. Here, we obtain two data points. So 0, 120,000 and 10, 0. Okay. So similar to the last example, we want to calculate the rate of depreciations. Okay. Then the rate of depreciations is, so rate of depreciations is equal to y2 minus y1 over x2 minus x1. So this is x1, y1, this is x2, y2. So you have 0 minus 120,000 divided by 10 minus 0. You should have negative 12,000. So from here, you can write the conclusions that the price of the machine is reducing at a rate of $12,000 per year. So the price of the machine is reducing at a rate of $12,000 per year. Okay, so you have the slope, right? You have the rate of depreciation. So now can you write down the linear functions? So you have the slope, you have the y-intercept here. So this is the y-intercept. So the b value is 1,000. Therefore, the linear functions is capital V of t equal to negative 12,000 times t plus 120,000. So that's the linear function that you can use to fit into this database. Any questions? We good? Okay. Now part B. What is the implied domain of the functions found in part A? So what is the domain of this function? You got it. You got it, right? I believe that you can do this one. Read the problem carefully. Yes. 0 to 10. Right. So 0 indicate that the original time. 10, t equal to 10 is when the value of the machine becomes 0. So when the machine becomes 0, there's nothing. So the implied domain of the function is from 0 to 10. Now, the implied domain of the problem will change depending on problem, of course, right? You good with that? All right. So for this, the implied domain of the function is from 0 to 10. Or you can write t is between 0 and 10, including 10 values. Any questions here? No. So what are we dealing with is linear functions, and you will learn later on the domain of a linear function is always from negative infinity to positive infinity. Okay, so that's the fact. But in this particular context, well, the implied domain, because we just care about when t equal to 0 to t equal to 20, sorry, 10. So therefore, the domain is between 0. You okay with that? All right. Now, moving on to part C, what is the book value of the machine after 3 years? Okay, so in part C, we're going to do another interpolation process. Okay. So given that, given the linear function, when t equal to 3, what is the value of the machine? So given t equal to 3, we get that v of 3 is equal to negative 12,000 times 3 plus 120,000 equal to I mean, even though if you give me the correct answer, that's more than fast. But do you I did want you to understand the process of plugging in the value, choosing the wrong, choosing the right value, choosing the right functions. Those matter as well. Hopefully you understand why. All right, so if you do the calculations correctly, you should get $48,000. That for part C. Now for part D, when will the machine have a book value of $70,000? So in part D, what we have is the book value. So capital V is equal to $72,000. What are we looking for? Looking for T. Okay. So what is the value of T such that capital V is equal to 72,000? So given V of T equal to 72,000, we get that V of T equal to negative 12,000 T plus 120,000 equal to 72,000. Now, can you do a quick calculations and give me the value of T? I know that for this, we have to use a calculator. But if you can do it in your head, it's a lot better. T should be a very nice number. 4. So t is equal to 4. What is the unit here? Years. Okay. So draw conclusions here. So to say that, you can say that after 4 years, the machine or the book value of the machine is $72,000. So after 4 years, the book value of the machine is $72,000. So there are many other applications that use Boolean functions to fit into the data sets, but we're not going to have time to cover a lot of applications. But if you happen to take a accounting course, a business course, an economic course, the linear function will probably gonna pop up every now and then. So it's important for me to know about linear functions in general, and because it's can apply into a lot of things in reality, not only in physics, in chemistry, in biology, but also in business area as well. Okay, now we're going to move on to another function. It's called quadratic functions. This is where you have the highest power for x is going to be 2, degree 2. Sometimes we're going to call quadratic function as the polynomial functions of degree 2, right? And we're going to look at the function. We're going to do some graphs on the functions. And if we have time, we're going to cover some applications.